good afternoon to all the participants present over here. Myself, Professor Naveen Kulkarni. I'm working as assistant professor in electrical engineering. On behalf of our department, I would like to welcome all the participants of this online FDP for our afternoon session. So for this session today, we have with us our resource person, Dr. Ranjan Kumar Behera sir. So he is professor in IIT Patna. He completed his PhD. His areas of expertise are power electronic circuits, control in electric drives, application of nonlinear control theory, renewable energy integration, and many more areas. Sir has published more than 50 plus articles and he has citations of more than 500 plus citations. His H index is 10 and I-10 index is 11. Sir, we are very privileged that today you are with us, sir, and it's a great pleasure to have you as our resource person for our session, sir. On behalf of our electrical department of SGU, once again, I would like to welcome you for this session, and also I would like to welcome all the participants of this FTP, sir. So with this, let us proceed with your proceedings, sir. I request all the participants to join and participate actively with us. Thank you, sir.
Thank you very much. Thank you, Professor Naveen, and thank you, Professor Ranjan also. So I am very privileged to be in your call in this webinar. So today we will discuss an advanced power converter control for solar and wind application. So you are able to hear me, sir?
Yeah.
Okay. So I am today this as a person, I am a completely hardware person. Okay, so I generally develop all these hardware modules. So completely generally we develop our own plant and we develop our own technology. So before going to that, this is how a journey of my life, that I did my BTech from NIT Rourkela, MTech PhD IIT Kanpur, and then I worked in university in General Electric, Hong Kong, and also, yes?
Sir, sorry for disturbing. Actually, your screen is not fully visible.
Oh, not visible.
Full screen mode.
Okay, just a minute. Yes. This is.
Can you share, sir?
Okay, I'm. Now visible, sir?
Yeah, it is visible, but full screen, you can make it full screen so that.
No, it is full screen only.
Okay. Then I don't know. Okay, continue, sir. Okay.
Is it changing, sir? Now
No, what happened? You have to select one by one slide so that it is changing. So in the left side.
I think there is some problem here. Maybe I will do one thing. I will make it PDF, and then only you can. In PPT and Google Meet, there are few problems come sometime.
Okay.
If it is not properly compatible, then it becomes very difficult to do this one. So in 2 minutes, I am just.
Okay.
I will connect. Okay. So Okay. Sir, can you allow me to present? I think
What, sir?
you just allow me to present
Okay, it
this.
is Sandeep, sir.
Yes, sir.
Anyone is presenting already? Just check it.
No,
No.
no.
Okay,
No one is
okay.
presenting.
Now it is coming.
Okay, okay.
So, you please allow me to give, allow me to share my screen. Please allow me.
Sandeep, sir, check it. Any request has come?
Full screen mode. So you must get grant permission in order to screen share.
I
So
think
can
some
you
info is coming.
screen sharing? You need to allow me, I think.
Sir, okay.
No such request here, sir.
Sir, Sandeep, sir, any request has come?
No, sir.
No, sir.
You must grant permission in order to screen share.
Sir, can
Sir,
you
make
once?
make him the
I was
co-host.
just
If you make him the co-host, is able to share the screen.
Okay, but he was previously sharing, no, ma'am.
Okay, okay.
But only the problem is he cannot able to show full screen. Sir, is it okay now? Sir, unmute. Unmute your audio.
again it shows you must grant permission from for screen sharing. Can you allow me to do that?
Sandeep, sir.
Can you take the PPTs from sir?
Okay, what happened? 3 IST login is there. Maybe due to that, I don't know.
No. That will be not the issue, sir. Ranjan sir, can you share your PPT with Rajin sir so that we can
Yes,
manage it
yes,
from.
I can
Okay.
send him.
Sir, sir, please send the PPT to my login. Already I have shared the mail ID.
No, actually, this will be very uncomfortable. Actually,
Okay,
that
okay.
is what.
What is the problem?
You just allow me. I think you can. I'll send the PPT after this because while presenting it will be very discomfort when I'll ask all the time. Please change this slide. Please change this slide like that.
Yes, yes.
Mm. So anyway, I am sending you.
Okay,
Okay.
okay.
I am sending you in the ISTE FDP 2021. Okay.
Okay, so okay.
I am sending that one.
Okay.
But you please do that one. It will be good when I will present. 21. Sir, I have sent in your this thing. Let me. No. So just allow me to present. Okay.
Sir, I want to.
Yes, now it is working, sir.
Okay.
Sorry, actually.
Okay, no problem.
Now is it full screen?
Full screen. Yeah, fine.
Okay, thank you. Sorry for being late.
No problem, sir. No problem.
Generally, I never go to class also, nor I allow anyone to come late also. But today there was a meeting with the agriculture minister of Bihar state. So our director was also there, so he told remain for some time. So sorry for that.
Okay, no problem, sir. No problem.
So today we will discuss control for solar and wind application. So after each session, I will ask if you have any question. Especially, we work more into the hardware rather than software development. So hardware always it is when you work, you find many problems when you work it. For example, a solar plant in IIT Patna, when we put 2 years that what kind of solar panel is required, what kind of structure suit, because even if the structures, you need to understand the structural engineering where this much of weight will be there and 200 kilometers per hour will flow, how you will design the structures. That is, although we get from the company and they put this solar plant, but these are not reliable unless you do not design and not understand what they did it. That's why the solar panels or solar plant are not sustainable. So when I was working with the around 50 megawatt solar wind turbine, 50 megawatt wind park, we have done for the Hong Kong, and as well as I was working with the sometime in the USA. So journey of my life, I did my BTech from IIT Rourkela, MTech PhD. Then I was working with the GE, General Electric Hong Kong and Bangalore. Then I joined in Tennessee Tech and then Pretoria University, South Africa. And then I am here at IIT Patna. So we work on solar wind drives, high power drive, wireless power transfer, smart grid, and electric vehicle design. And one of the vehicle we designed recently, it is only 20,000 rupees. You will get a three-wheeler vehicle. So we have designed that 3-part, and also we have many products we developed also in the lab. And that intelligent solar pumping, other so many products by our simple students, they could able to do that. So we have a small book I have just this year published, Power Electronic Drive in Advance. In this book, you will start from fundamental up to the advanced dual active bridge converter, solid state transformer, everything is there. So these are the outline. I will speak at last. I will give you a project which is we installed. One of the last project was that in Port Blair Air Force Station, we put 1 megawatt solar plant and completely designed, and it is investigated and is designed by IIT Patna. And starting from the cabling to the grounding to the bus bar design, and also putting the structural design, because in those places structures are very important, because at the sandy place you cannot fix a structure, and after some time that structure will start vibrating. So that is what the challenge the Port Blair, and those type of challenge we cater and we design. And I'll go through some, you must have seen voltage source inverter feed grid connected PV system, but current source inverter feed grid connected PV system, there are very few. So that is why it is very essential in understanding of CSI feed, I'll speak. Then there are few technologies which we just recently published in the then we will see some wind energy if some time permits. Okay. So this is a current source inverter fed grid connected system. And if you see here, this is the our laboratory picture actually. If you see the current source and voltage source, all of us we know because all teacher and students, everybody knows what is current source inverter, how to convert it from a voltage source to current source. Okay. So like that, if a PV current source inverter has amount of a lot of advantages because this advantages caters the robustness into this inverter system. So that is why, because the current is unidirectional, so most of the time we are very happy with this type of converter system. So current source inverter fed, what are the problem? Current source inverter, although we know many disadvantages of pulsating, there is a pulsating current, pulsating waveform in the voltage source, but here in the current source inverter, one thing is very good that when you use for solar plant, you need to design the proper controller and then it will work. So this is a PV source and we have a series inductor and a constant current, and always this three phase current source by using IGBT, and you can see that there is a series diode. Series diode is used just to make the device as a unidirectional. A bidirectional device is made as a unidirectional device, and then it is feeding to the grid system. So these are very important thing, and there are few filters are connected. LC filter is connected, and I am not going detail into the mathematics. I want to just give the fundamental concept where you can think more and you can explore more into this one. So if you see here this block diagram, you have a current source inverter. We are feeding to the grid, and from three-phase PLL, we get the angle information, and from angle information, you can see that you do not require a separate MPPT algorithm. MPPT algorithm is embedded within the inverter structure, so only single stage inverter can work both for MPPT and both for maintaining the frequency as well as phase angle as well as synchronization. That is why this is all in one. So when we have a MPPT structure, sir, is it audible to everyone?
Yes, sir. Yes, sir.
Okay. Thank you. So when we have harmonic are like a oscillation within the system. Even though, like in your house, a boy, he don't obey anyone. If you give 2 slaps, he will create more nuisance. I have seen in USA, there was a kid in some place, so in the one's house, and his father became very angry and just touched his ear. And when he heard this kid break all these glass, they are so furious. And that is called uncharacteristic harmonic. Okay. So anyway, these are the proper switching model we need to design for current source inverters. And these active switches, you can see that there are 6 active switches and 3 null switches. Okay. And these null switches and active switches combination can operate this complete system. Then after getting the modulation index M, then you have a decoupling, then gate signal, and then we feed to the switching signal. You can see here, this is our reference value of IDC current. In the case of your voltage source inverter, you have the reference is a voltage source. And here, the reference is a current source. And this current source inverter, okay, they actually, this current source inverter, we have a reference as a current. And you can see that this is the tracking to the exact reference. And you can see that this voltage current are unity power factor. Unity power factor means, what do you mean by unity power factor? That means we say it is a utility friendly converter. Utility friendly means, you see, Ganga river flows. So when Ganga river, you go to Uttarakhand, it is a very beautiful water. Like I go to, generally, I visit every year to Pauri Garhwal. There is a college called GB Pant College of Engineering. So whenever I go, and I go to this Devaprayag, and I go and take water and take sometime put some water and drink some water. Very pure water, Ganga river water. But you come to Kanpur, when I was studying as a student, we used to go. There are Itawa, all this leather industry, they put their all water into the river. And when they put it, it became polluted. That means whatever water they are putting in this river, they are not utility friendly. And what is that? That means they put the reactive energy to the water. Similarly, when you operate any power electronics converter, it is not feeding what is creating? It is creating reactive energy to the system. So reactive power means, what do you mean for a common man? Reactive power, like we have a newborn kid. When you take a newborn kid, take alone the kid, we don't take the kid alone. We take little cloth, and that cloth we put the kid, then we carry wherever you go, or some warmer you put, and then inside kid is there, newborn kid. So if you see the cloth is not important. What is important is the kid. Similarly, in the power system, the active power and the reactive power, but the active power is needed. You are paying for active power. For in your house, you pay for active power. Active power is needed. But what is the use of this reactive power? The reactive power is like a carrier. Without reactive power, you cannot carry. So similarly, like we have a cloth, similarly the active power is carried by this reactive power. So that is what, when you operate the converter system, with the unity power factor, you have zero reactive power. It operates at a maximum power point because cos phi is equal to 1. So this is, you can understand that whatever the maximum power transfer theorem we study in our book in the first year of electrical engineering, the same thing we are doing here. Only we give the new name as unity power factor system. Okay. Anyway, these are the modulation index, where this modulation index is varying from 1 to 0.8. And modulation index also, there are nonlinearity, but we don't go beyond the limitation of 1. Okay, above 1 you will go over modulation region, and where that is altogether different concept altogether. Then this is our DC link voltage. You can see in case of VSI, the DC link current is exactly like this. But in case of CSI, the DC link voltage is exactly like a VSI voltage. And these are the output current, and you can see that they are 120-degree phase apart, A and B and C phase current. And after filtering, you can see that both voltage and current maintain unity power factor. So unity power factor, that is what it is said. You can see that TH is less than 5% of this current. And these are the output filter inductor. This is voltage across the inductor and the capacitors. And then filter capacitors in the phase A, you can see that these are the waveforms, and you can see that the robustness of the PLL, phase lock loop. What do you mean by phase lock loop? For example, you are going in the relay, in the racing competition, there is a running competition, there is a relay, okay? You go by jumping to many hurdles and give that, whatever you are carrying, that relay to other. Like one person take and other person also wait there and quickly take that one and go to reach other person, give other, like that. So similarly, this PLL also exactly like that relay system. So what kind of relay? It is not like this relay. PLL is the system where it will just lock the system to the desired frequency level. For example, here I have given 50 Hertz is our Indian standard frequency. At 50 Hertz, it is locked the system. And you want to change that one for sometime 48 Hertz, I have changed. So you can see that it is also tracking to 48 Hertz. And this is what the phase lock loop means. Always it is fixing with the input phase voltage or output phase. So that is what PLL, and that is why it gives the information of the theta, the position of voltage vector in your space. That's it. And this is the what we have done the inverter. This is tested with the laboratory single phase one, and we extended for 3-phase one. And then hardware result are, you can see that it is completed perfectly. You can see that there is no current waveform. You can see these are hardware of that one. So this year we have already give all this thing we designed for the course inverter feed PV system. Okay, so very few papers you will find current source inverter feed, because there is some disadvantages also because of the switching. Like in VSI, you have a wrong switching, no problem. But CSI, one wrong switching can create havoc. Complete converter will damage actually. So that is why CSI people are very fearful, because one IGBT cost nowadays around 1,500 to 2,300 rupees one module. So they are little fearful why to use this one, and there may be some problem. So this this research is on. If you have any question, you can also stop me anytime. Anyone has, and I want to ask any fundamental things, then you can ask. You can stop. And we did an hysteresis current controller, a grid connected system with active damping. Okay, and this same paper, it just appeared in the Early Access and Industry Application Society. And this is a single phase inverter. And I know that all of you know the single phase inverter. And also you know LCL filter. I know that all of you integrate with the grid with a transformer interface. Without a transformer interface also, I know all of you know it actually. But I want to tell one thing in this one, that there are three kind of frequency associated system. One frequency, like you are seeing here, a single phase inverter, H-bridge inverter, and feeding to a simple LCL filter, and LCL filter is connected to the grid. From grid, we get the information of theta, okay, through PLL. And then we use that one in the reference current generation. And then we send through a regulator or the proportional and resonant controller. Why resonant controller? What is a PI controller? What is a resonant controller? A very lot of differences are there. PI controller, sometimes your integrator may saturate. So saturation means like some, if you see, saturation means if some student or someone's child, if they have beaten them so much that even if in angry you beat them, they will laugh at you. Because they have already saturated by beating every day, they get beating. So they are saturated, okay. So like that, even though you will beat heavily, still they will laugh at you. Why? Because they are habituated to that. That is called the saturation level. For example, you take 4 rasgullas and 5th rasgulla, you have already saturated. Oh, no, I don't require more. So that is called saturation. Similarly, a simple integrator has a problem with the saturation because of the offset, okay, sometimes. So, but if you simple integrator and if you use a simple low pass filter, that will create a reduce some of the offset problems, okay. But when we have a proportional plus resonant controller, that time PR controller will give us the resonant controller. It is a second order system. And when you have a ripple content like a sinusoidal, or for example, current tracking, you are here seeing the reference current and the actual current. And the difference is that is your current tracking error. So if the current tracking error is in the shape of sinusoidal, so PI controller will destabilize quickly. When you put a resonant controller, they can take care both DC component and the little bit AC component of the system. That is why the resonance controller are most important. How to design this resonant controller, that is also a big aspect, big theory. But anyway, I am not going to tell all the detail of resonant, but I will tell. You see here 3 frequency associated. First frequency is the switching frequency of the converter system. Second frequency is the resonant frequency of your LCL filter. And third frequency is the sampling frequency of your computer where you do this hardware implementation. So when these 3 frequency come into picture, and 3 frequency has a big correlation, although I have not found out till now. And one of my students, I told them to study on these 3. These 3 itself can make one PhD. Just listen, what is the switch frequency, what is the sampling frequency, or what is the resonant frequency. Although most of the time we use it, it works also. but we do not know the correlation between all three. And that is why these three, finding the switching frequency, a resonant frequency, and the sampling frequency, there are a lot of correlation, and we found out few things, and that because as soon as you have the sampling frequency, then there is an offset in the system, completely it will create the more resonant frequency also. Anyway, there are a lot of theories in this one. Then we model this LCL filter, a simple filter, and complete unit is designed. And we have a Bode plot, okay, to find out the stability of the system. So you can design the LCL filter by using this also. Find the bandwidth. From bandwidth, you will find out what is the LCL filter parameters also you can find out. So after that, when we have this filter design, then you can find out the transfer function of this one. And so after this, I have already shared these PPTs, and I think Sir will circulate to all of you. Anytime you will get any doubt, you can simply mail me also. So I will be happy to answer any questions, okay? So this is the simple transfer function. And after finding the transfer function, how we design the hysteresis current controller. Why hysteresis current controller? We know that it is a nonlinear current controller, but we analyze all hysteresis current controller as a linear thing. Hysteresis is a nonlinear system, like a slider. Slider, you go this way and come other way. So similarly, the hysteresis current controller also has the nonlinear controller. And if you want to know more about this one, we have long back published a paper, frequency domain analysis of AC/DC converters for a utility friendly applications. So that is in IET, I think, that paper. So that paper I have explained very nicely that how the nonlinear, by using the way of nonlinear technique, how you can find out this thing. So anyway, the hysteresis current controller is this one, and we have a resonant, and you can see that there are different hysteresis band. You can create your own hysteresis band. Like here you see, one is single band hysteresis. You can see here the 4. This is our single end, okay, single hysteresis band, and this band can create a very beautiful, you can see that it moves, and when the error increases beyond this plus HB, so it gives 1, and it's less than minus HB, it gives -1. That means it operates both the diagonal switches and upper the two diagonal, and in minus also to other two diagonal. So the output waveform is voltage is a bipolar. Bipolar, you know, I think single phase inverter, you have a bipolar modulation where you get 2 pole in the output voltage, and unipolar, that means you 1 pole in the output voltage. And single band and double band hysteresis current control. And we found out based on this one, switching frequency, because if you don't find switching frequency, for example, hysteresis current controller is a variable frequency control. So how you will find out the estimated frequency? The estimated frequency you can find out by this formula, and this, to get this formula there are a lot of derivations. Then we have a double band hysteresis current control, and this double band, why the band increases more and you can also decrease more also, okay, within that switching band it will control. So when you have increasing the band of this one, you will see that your switching frequency decrease. You see, F is inversely proportional to H by the band of this hysteresis current control. And you decrease this one, the frequency will go high. Okay, that is why our IGBT, we can operate up to 20 kilohertz. That is why we try to operate this, to apply the optimal switching frequency to that one. Okay, so that it should not cross beyond 20 kilohertz. And then this same thing, we have designed a modified hysteresis current control technique. And that hysteresis current control technique, you can see that these are the sequences. Based on the sequence, we find out the logic diagram we implemented by using this simple logic diagram and OR gate and JK field flow. And signal, you can see that the output voltage is a unipolar one. You can see unipolar 0 and 400. So the unipolar voltage, okay, you will take fundamental one means it can happen. This is your fundamental, it will come. And this system is implemented by using Opal RT, okay, plus hardware setup also. So then we have a LCL filter and connected to grid through a interfacing transformer and local loads. You can see here in this grid we have this bulb as a local load. So the local load can be used and LCL filters, and this is connected to our Opal RT and a DC link, and it is connected to the grid. And these are the few simulation results. You can see here the single band hysteresis band. You can see at zero crossing, this gives, you can see here at zero crossing, the frequency is really very, very high. Okay, but where in the modified one, you can see that at zero crossing, there are very low frequency. And there you can see here, the zero crossing low frequency. This is the how you can design any kind of hysteresis current controller. You implement and study what is your benefit you are getting. So like that, if you see here, we are changing the reference current. For example, here we have changed the reference current at 0.23. Okay, so and suddenly this changes actually. So reference current changes with respect to, you can see that there is sudden change in this current, and when you are stepping up also, the reference, it is tracking to the reference current. And that is why the hysteresis current controller, they are said they are the most efficient current control technique and very fast current control technique, fast current, very quickly. Like you give a slap to your somebody and he also give a suddenly one slap to you. Okay, like that. So tick for they like that. So you beat them and they will also beat you. Okay. And these are the few hardware results where we implemented. Here you can see that in the figure 11, you can see that we are changing both the current reference and suddenly it is tracking that current. Okay. And like this, you can see that the current is, you can change the current and dynamically the current change, but it doesn't affect on the voltage. So that is why the hysteresis current controller are a very popular method. And although it is very simple to implement, but one problem is that it has a variable switching frequency. That is why you cannot design a particular filter circuit. It is very difficult. So what we do, we design first a basic filter circuit, then we try to tune those things. Okay. And these are the few this. Then, so do you have any questions till now? Or if you have any question, or you need 5 minute rest also, it is okay. 1 hour over. So if you want, you can. Sir, do anybody has any questions, or we will continue, please? If there are no questions, we will continue. Okay. Okay, ठीक है. Thank you very much. So let me continue. Okay, so at last we will put some question anyway. Okay, so today we will also discuss few fundamental things as the high power converters when we are integrating with the grid in the multi-phase level. Okay. So first thing is the grid interfacing. Okay, if we have a grid interfacing inverter circuit, grid interfacing inverter circuit is always they are one of the important parameter, because you know the drives inverter, they are different than this because solar inverters are always the many protection system need to be embedded within them. And this grid interface inverter has a very important role in controlling the output voltage, current, and power, quality of power. There are many control strategies for power electronics converter, especially VSIs, and linear control and nonlinear combined together to become the most frequency concept of industrial drive. And there these are the logic, and this is the complete unit actually, proposed system, constant frequency hysteresis current controller. And you can see here the VDC1 and IK minus I VDC1 and VDC2 is fed here. Then actually you pass through a PI controller, and then you have a voltage information, then theta, then signal generator, the give. So this complete unit is implemented, and this is the fed to this switching logic, and switching logic used to operate the 3-level inverter circuit for grid connected system. So if you see here, very fundamental that when current ripple analysis you come, you go on changing the current ripple or modulation index, you will see, or you change the amplitude of the ripple, so carrier amplitude, you will see that in all the case, you can see that current ripple is very less, okay, at 0.5 normal operation. So that is how this at 0.5 is the current ripple is 0.5. Okay, so that way, that is how we can alpha is chosen as 2 and H is chosen as 8. That means that is given that is the H alpha and H is 1. Now, when you have a switching frequency, you have a carrier amplitude, and the switching frequency, if you see here, carrier frequency and switching frequency, they both are nearly equal. Why? Because both are nearly equal, because as soon as the carrier frequency drives the switching frequency to operate that at that point. So you can see that at 10 kilohertz you get minimal, at 20 kilohertz you get a minimal the switching ripple. So now you can see here I have put some figures and the hardware result of that one. Just okay. So this is the hardware result. You can see here, both current and voltages, they both are in phase. And they are sinusoidal. And you can see that both the voltage of DC link, VDC1 and VDC2, they both are maintained constant. Okay. And the third one is current tracking error, which is shown here. It is very beautiful. You can see that these are the current tracking error. Now you see, we want to operate this current controller at unity switching frequency, or switching frequency is at 1 kilohertz according to the design. So the switching frequency, you can see that the average is nearly at 1 kilohertz. And then magnitude of this current, and this is the stability margin. Okay, this is the system stability plane plot. Okay, so different plot, so different frequency of the system. You can see that frequency starts from 6 kilohertz to 10 kilohertz, and this also exactly follows that. So when we compare this one, you can see that the switching technique or this hysteresis current control is that the settling time is 0.05, 0.08. Proposed the frequency hysteresis current controller is 0.085. So the band is very limited. So now we have another part as this is a very practical system. When we implemented, we could able to understand that this practical implementation is very, very important. So when we see here, this is modeling control, and is of the 10 kilowatt grid connected solar energy system. So what is this 10 kilowatt grid connected solar system? Because this description or the description of the system I will tell, and modeling and side effects. For example, this figure. This figure, when we are saying, you see a sine wave and there is a current waveform. And this current waveform, you can see, is like a triangular. So when you get this one, so when you have like this triangular waveform, then we have a problem. Okay. So now the harmony create a problem in the solar system. There are different harmonic, okay, and this stand means the power quality system operation. This is a European which speaks about ISTE and the current harmonic and voltage harmonic. And the European understanding speaks about the total harmonic to 8%, including up 8 harmonic. So when we implemented this proposed system, it is a simple 10 kilowatt system, and we have an MPPT, and then we have an inverter and connect into the grid. Now this inverter, here we have model, similarly LCL filters are there, and we model this complete inverter, including this filter circuit. Now this is the controller design. We design the controller, then design implemented. This you can see that the complete unit we design, and you can see the current waveform also in the monitoring. Okay, in this monitor there are these current waveforms. Okay, and then we have this storage battery, and we are feeding this from this solar. Now the performance evaluation, you can see that the phase current of the grid at loading or partial, at low loading or partial setting, you can see that this current is not actually a sinusoidal current, and this when you have a full load condition, you can see that both current and voltage are sinusoidal in phase also. The current PhD, and you can see here, then you have a partial setting or low loading. Okay, you can see that the current is distorted. Current be distorted because of the low loading or partial setting. Now practically we have here around 1 megawatt. So I was asking to the state electric board, I asked them, this we are feeding to the grid also sometime, so you should put a net metering. He told me that Dr. Behera, you are only creating noise to our grid. You should pay more to us, not we should pay. So like that, he was joking. And this is how the purpose. So this is the PhD. You can see that it is the performance evolution in the there are. When we are feeding the full load condition, you can see that both current and voltage are uniform and they are feeding to the. And this is which is less than 4%. Now this is also during grid feeding actually to the system, and this is when the grid is feeding, giving to the DC link. Okay, so this is the opposite direction. So anyway, the tender we have implemented, and it is very modeled, and LCL filter is carried out, and both simulations are given here. And this, and there is another which is called the concurrent design methodology. See, concurrent design methodology is for the grid current feedback activity. So this was I in the America, the process So this work we did at that time. The first thing is the system. You can describe the system. You see it. What is the difference between axial field this one? There is only one little difference. Okay. Active component. So what is active damping component? When we see here, we have a PLL. PLL gives us information about angle. Then we transform ABC to DQ. And after that, we have a current controller. Actual current and reference current are subtracted, passed to a current controller, and that current controller gives a modulation index. And here what we put active damping. I told you in the first, I told all of you, we have 3 frequencies. You have a resonant frequency, switching frequency, and another is a sampling frequency. Now by putting this active damper, what you are doing, you are actually you are aiding the forward gain in the system, K2, the system. So and it also gives you the different, for example, how we design the controller. We design first, we try to find out the state space, then we design that. But here, simultaneously, you can have a damping controller and the current controller. So that is what here it is given, the effect of the issue of LCL resonance, then effect of system parameter, and passive damping and active damping. And then active damper, you put dynamic response, low resonant frequency of the LCL filter. So simultaneously, novel technique need to be designed, and simultaneously design of an active damper and current controller. So active damper means you have to measure the DC voltage or DC voltage of the capacitor across the capacitor. And then this is completely designed, the controller. Now when you see here, we have, you can model the complete system. This is very simple. This is ABC to D transformation, and alpha beta to DQ transformation. This is just coordinate transformations. Now we come here, we have a LCL filter, we have a, and this is diagram. Now this block is VAN, VB, and VCN. Okay. Now this is the switching sequence. Okay. I am not going. This everybody can equation. Okay. Then you design control variable. Demand control variable. What is your desired response? Okay. If we have a desired response, then automatically, if you good desired response can give good response in the we have conventional efforts. First thing is design the controller. How to design that we will see in the letter A in the DA part. The second one is the active damping system. Active damper control system we design. These are the simple parameters. Omega is your sampling frequency. Omega C is your crossover frequency. So these are the few mathematical derivation where we can do like this. And these are parameters. Parameter. This is DC bus voltage, grid voltage, and these are the parameters. And when we put this one for different the frequencies, so you understand that the controller parameters are brought from here. So you see, root cause of the closing start, at any point you that means in our sometimes if it will not come to 0, so whether it is stable or not, in the near the 0 region, but epsilon, if system will reach at least at nearby neighborhood, then automatically it is stable, and that is all about the control. And all these three are for different parameters we have studied. And this is the margin. You can see the 6 dB gain margin and 3 dB gain margin. It is designed. Now, both this current system, you can see here, there are 3 dB, 6 dB, where 6 dB quickly it damp out the transients, whereas 3 dB, it has its own inertia. Okay. And this is here you can see that the D component and the Q component of the system, this one. The D component current and Q component of current is given here. So this is the simulation result of the case A when grid side inductance is doubled and control parameter is related to 6 dB gain. So this side is 6 dB and this side your 3 dB. You can understand, you can see from the response is the 6 dB. Okay, that means to increase the gain, then this became less oscillatory. When the gain margin, for example, if your room is very big, you send 10 people, 50 people, 100 people. Room is small, even 10 people, they will become suffocated. So similarly, like this, about this. Now this is implemented with our and you can see here, dB, the 3 dB exactly, both current what we have seen, that and this current both are matching each other. And it is actually, you can see that there is a reference current change. So this change and it is tracking. But when 3 dB gain margin, more in the more current ripple and more time for stabilization. Solution, we have designed a very beautiful control technique and based on decomposition methodology. Okay. And this one is independent of phase margin and gain margin. The controller what you design, they both are independent of phase margin and gain margin also. Few parameters also, no expertise parameter tuning is needed, and demonstrate the validity and effectiveness of the property. Then there are also low voltage ride through, which is very important thing in our PV system. So I will not go. Low voltage ride through means when your converter is operating at a very low voltage, the converter should be turned on and connected with the grid. And there are a lot of low voltage ride through technologies. And these technologies are in the normal operation, we are feeding to the load. And this is a simple experimental system where we implemented the complete DC microgrid structure. And these are the hardware result. Okay, you can see here. This is the hardware result. Okay, this is converter. Then this is your phase lock loop. Okay, so grid synchronization for phase single phase system. Okay. Now this is our conventional PLL, the SOGI, second order generalized integrated PLL. There are different PLL. Okay, so you first find out the transfer function, then try to find out the blow report, then you implement here. Then CSOGI PLL is a cascaded one. So you can find out the transfer function and put the blow product. So these are the, one of my student, he studied all kind of PLL structure, and this is the modified SOGI PLL. So these PLL are for synchronizing with the grid. Okay. And to find out the angle information. Okay. First thing is angle information. Then we design this complete system, okay, linearized model. And then we did a parameter, okay, we try to find out the what are the different parameters, PLL methodology in that different parameter. You can see that every value, okay, here you can see here the most important thing is that this these values you are, when we are comparing, you can see that these values are in our proposed one, it is very less. So when we see here this TS, you can see these are the parameter variations, V alpha and V beta. And these are the few result, okay, simulation result and all kind of PLL system. And then these are the hardware result, okay, where we used this PLL for developing the hardware one. So you can see that settling time is, the modified one is 40 millisecond, okay. And then frequency overshoot in hertz, you can see that very minimal is at. So these are the few findings. Then we have a PR controller, proportional and resonant controller, okay. So this is the structure of resonant controller. You can see here PR is equal to KP plus KR, okay. Now if you see here, this complete unit is this you find out the transfer function closed loop and find out the stability. Then this is connected with the transformer, okay. Last time we have no isolation transformer, and these are the parameters where we want to experiment. And then we implemented in a PV curve, okay. This is your PV system, and this is the power, and this is voltage curve. Now you can see here the DC link voltage is fluctuating, and although the irradiation changes, but the DC link voltage maintains constant, okay. Now in the conclusion, SOGI PLL has fast dynamic response, and they are generated, and it is also help us to design the proper controller. So now we studied all about this solar based system. Now we will discuss about the wind power, okay. We wind power installation. Actually in Bihar there is no wind power, but we can design by using emulators, okay. This is this is modeling and of the power converter. Two, this is double fed induction generator. What do you mean by double fed? Double fed means you are feeding one side and another side you are taking thing. Okay, double fed. You can see that from the rotor side we are feeding. And the two converter, one is AC to DC converter, and another converter is from DC to AC converter, rotor converter. And this is one converter. The first grid converter is called. This can give you the operation, and this converter can give store. You can store and also keep energy and release energy. So like that, modeling is the objective of the control of converter are voltage regulation, bidirectional power flow, operation at any power factor, low and harmonic. Now this you have an input on the rotor side and grid side. First thing we will model grid side converter. So grid side we are in inverter, okay, you can see, or AC to DC converter. And we can up to this capacity DC. Then from the grid we have 6 switches, and then we control this one and operate this one. So first we will see the grid side one, then we will see the rotor side, and both combined together will form the double fed system. Now this can operate at any power factor, at unity power factor also, okay, and leading power factor and lagging power factor. How it is possible, lagging power factor or leading power factor? This is possible because because this will you can operate your accordingly. If you operate at leading power factor, this can also operate at leading power factor. So anyway, this we can do the mathematical modeling of the system. After modeling, you can write down the equation. Okay. So I don't think that this is very difficult. Everybody can write down this one, and then we convert from ABC to DQ. Okay. Then we model this one, and you see these are the two equations, two side dynamic equations. But the problem is that we have this form where the coupling form comes into picture. So this control we designed based on this transfer function. And this is our block diagram. You can see here when you have a reference DC voltage and you measure the actual DC voltage, compare this PI controller, and this PI controller will give ISQ, and ILB or IFB is your this current, quadrature axis current. So when you pass through this PI controller, and there are some negative blocks where you can negate your amount, negate your signal here, then pass through this AQ to ABC transform, then to or alpha beta, then C. So most important thing is the controller design. So how to design controller? If you see with this one, you have a two loop. One is your inner loop, another one is your outer loop. When you want to design the controller, first you consider the inner loop first. When you have an inner loop, then once the inner loop is controlled, then outer loop you can design the controller. So this inner loop, you have a PI controller, then we have a transfer function. You can see that plant transfer function. And then we have a RL low pass filter. A2 divided by 1 plus A2. Okay. Complete unit. Okay. When we find out the current control loop, this is a current control loop. And the current control loop we feed. Okay. This you can find out the parameters from this. And then this current loop are 0 in the system. You can see that 1 plus ST to 1 0. And 0 will create a sustainable oscillation in the network. So to remove that sustainable oscillation, we put a feed forward path, ISU. And this is modified the current loop. And then once current loop is modified and current loop constant K, 1 by K2 divided by 1 plus 2 rho S. And why we have taken this delay in the feedback? If you see, any delay, we put unit delay. Here. This typical thing is very important. First thing, when you have A to D converter, you measure the DC link voltage by using kind of sensor. For example, voltage sensor we use. Okay. So voltage sensor we use, and we convert from DC voltage sensor and pass through analog to D controller. When you pass a analog to D controller, delay of 1.6 microsecond, minimum delay of 1.2 microsecond delay. So when delay, your delay is associated with your feedback. So in the feedback path, that is why we have given a delay here. And then complete unit we have designed. And we have a simple this system. Then we designed the complete transfer function. After designing the transfer function, we find the body plot, the phase margin and gain margin. And after that, we tested machine. For example, here we have a grid side converter and charging this DC, and then we have another rectifier which is feeding this DC. So why we put two converter? One is we are having one converter, and another converter is for testing. For example, S2 and S1 is on. This BDC is charged to reference value, and you increase the diode voltage beyond the reference value, the current will flow to opposite direction of this grid side converter. So that is why it is very essential. Now we have a unit power factor. You can see this both voltage and current can be 1, and you can see that DC link voltage is constant, and then we have a IQ, ID current. And we have, you can see that there is a decoupling, because when you change the IQ, that when you change ID, then IQ. You can see that the leading power factor, you can see this is the leading power factor you can operate when the DC link voltage is higher than the reference. And we can have a lagging power factor when the DC link voltage is lower than the reference value. So this is our complete unit. We have installed this system, and Professor Gao, under the supervision of Professor Gao, it is a 5 kilowatt system. So you can see that these are the practical system where both voltage and current are unity. Power factor, you can see that there is a lagging power factor and there is a leading power factor. And then the rotor side converter you can model, and these are the modeling of the rotor side converter, and like this, and then this modeling can be done by using mathematical equations, and from this mathematical equations you start finding the power requirement. Okay, so power requirement you find out, and if you put here, you can see that power, the active power depend on the IQS and reactive power depend on the IDS. So that means complete decoupled control is achieved here. Okay, because like a DC machine, DC motor, when you change the armature circuit, there is no effect on the field when you change the field axis. So there is no effect on the armature circuit. So that way it is decoupled. So these are the few results of the D-axis rotor current and D-axis current of the response, and rotor current IR, rotor current IR, that is the response. So at this point we invited, okay, so these are the few references. And then we have done many projects. So I don't know that I can show you all display is designed by us, and proper suggestions are given for developing of this complete solar unit. And this is our at IIT Patna, which we have designed, and these are the another 1 megawatt solar power plant. And these are the one of the unit we put in different places in Bihar, and this is the place in the Araria district of Bihar, and this is another project which we implemented in the Boisali district of Toipur village. Okay, and we are supplying 50 houses, and it is smart control, IoT based communication, and this is microgrid. Now, this is our Port Blair station project. You can see these are the panels, okay? And these are the road structure, everything is given here. And this is the cabling, okay? How to make cabling, also another challenge in case of our solar energy. And this is the microgrid in Port Blair. This is our teaching learning center at IoT Smart Grid, Smart Building. And then this is the teaching learning center. Then we have these are the 3 modules, which is you can see one module is your communication, and the module is your power, and you are in the middle. Now here our students are installing some of the solar panels, and this is the wind for smart microgrid we designed, and you can see that we have 2 wind turbines. One is horizontal axis, one is vertical axis, and this crow comes. This solar unit is integrated with with this wind turbine. You can see here there is a crow sitting on this DC unit. This is very, as they come and just they make dirty to these panels. So anyway, we have a controller and feeding to the smart load. So we have also a few microgrid projects, and we have a hardware implementation. So I will show you some of my, maybe one video I will show you. If there is, so do I have more time?
Sir, 10 more minutes. Sir, you can take your time, sir. No problem.
I want to show 1 or 2 videos.
Okay, no problem. No problem. No problem.
So that
so it is for good. It is good for us. Please show, no problem.
So So the complete unit, how we have installed is given here. Okay. Okay, sir. Thank you very much.
Participants, if you have any doubts, please ask. Participants, if you have any doubts, please ask. Sir, I have small doubts regarding some of the points. That simulation, you are using MATLAB or any other software? Simulation.
We use, sir, MATLAB only.
MATLAB only. Then one more thing for interfacing with hardware. Whether you are connecting directly through DSpace or anything or separate hardware.
We have a DSpace micro box.
Okay.
And
okay.
we connect that one to the system.
Okay. Then, sir, next one, our alpha beta to DQ conversion. Usually we have root 2/3 and 2/3. Two concepts are there: power invariant and non-power.
This we did lot of research.
Yeah. My question is, most of the journal papers we used to consider it as net powers are same. Three-phase power is same as two-phase power.
Yes.
So accordingly, if you say, it will be root 2/3. That value will be root 2 by 3. So how in our alpha beta DQ conversion, I have seen your PPT. Sometimes we are using root 2 by 3. One time I have seen 2 by 3. So how we will change it according to any other parameters? Can you give some suggestion?
Yes, actually, especially in the drives, we have two kind of winding. Okay. One winding is a distributed and concentrated winding. Okay. Similarly, when we design a coupled inductor for our synchronous link inductance, if it is concentrated, then we use root 3 by 2. If distributed, 2 by 3. Actually, we have multi-phase machine drive. In that, I have seen in direct torque application, when my student was giving to mark. So I told him to study why we should use this or that. So he did a lot of research on that one. This is depend on the winding structure you are using. And there you can use 2 by 3 and where you can do this. So distributed winding where they are separated and there are distinctly number of turns are given. And in the concentrated winding there is a mutual inductance effect. That's why power variant is coming to picture. And distributed one you can take number of turns.
Okay, sir. Thank you. Then emulator, a wind turbine emulator, which emulator? How we are?
Sir, we have two emulator here. One is permanent magnet synchronous generator. By using, we have a simple DC motor emulating system. And we have a hardware project already. We have wind turbines. So we use that data.
Thank you. So one thing has come. Can we apply MATLAB optimization algorithm to maximize the output of solar system?
MATLAB optimization.
Yeah, can we apply MATLAB optimization algorithm to maximize the output of solar system?
In the simulation you can do that one, okay. But in hardware you need to, once you in the complete automated system, then you need to tune many parameters actually. So once I have seen when we design like that parameter, sometime if there is some no solar and one battery is discharged completely, that battery will behave like a short circuit. So there, although you are try to control the current, this side battery is collapsed. So that will behave like a short circuit. So a lot of problem when the grid integrated system with the battery storage are there. So you need to balance the batteries also that time. So that is why you need little tuning during the hardware.
Any other question? Participants? I think no other question.
Okay, sir.
Yes, sir. Yes, sir.
Please, sir.
Good evening to all of you. I'm Anand Kumbar, Assistant Professor at Sanjay Ghodat University. I take this opportunity to express my sincere thanks to our today's resource person, Dr. Ranjan Kumar Behera, sir. Sir, whatever practical things you shared with us, they are really very helpful to us. And to work with power converters in the area of wind, or it may be a solar energy conversion. So it was very nice experience to see the practical things. Sir, on behalf of Sanjay Ghodat University, on behalf of Electrical Engineering Department, and on behalf of all the participants, and on my personal behalf, I am very much thankful to you, sir, for accepting our invitation and sharing your valuable time and practical experience. Thank you, sir. Thank you very much.
Thank you very much. I also thanks to especially to Professor Ranjan Linus sir for inviting me. And second thing, I am in the online mode, so I do not know whether I could able to give something or not.
Nice,
so
sir.
I am sorry for that.
Really nice.
Nice, sir. Nice, sir. Nice, sir.
Okay.
and you focused more on practical things. That was really a nice experience for us.
Actually, anybody want any help, or many people they come here, we have all kind of hardware setup.
Okay.
So starting from multi-phase machine drive up to smart grid setup, everything is available.
Okay.
Anyone want to work here practically, they can come. They can do simulation in your institute, and they can come here and do the practical work, hardware, and they can publish the paper.
Okay.
We do not want our name to be published. They should come and learn here. That is our main aim.
Thank you, sir. Thank you very much.
Okay, sir.
Thank you for offering this opportunity for us, sir. Thank you.
Thank
also,
you.
I am very much thankful to all the participants for your active participation. Once again, thanks to one and all. Here I declare today's sessions, all the sessions are over. And tomorrow we will be continuing with new topic for this STTP at sharp 10 a.m. So all are requested to be present at 10 a.m. Thank you.
Thank you, sir. Thank you very much.
Thank you. So all these participants, please check the chat box there for today's session. Kindly go through it and update it, and we will also share to WhatsApp also. Please do now itself, so that tomorrow when we continue it will not be mismatched. So I request all the participants, please join at 10 o'clock tomorrow sharp. You will get an industrial experience of energy conversion system. He is a mechanical as well as engineer, as well as a little bit about electrical as well. So he will explain about the power converter. Wish you all the best. Thank you so much for the participants today. No. Yes.
Small request, sir. Please send the PPT if possible, sir. Today's class PPT.
Okay, sure. We'll send it, sir. We'll send. Now it's okay. Thanks. Okay.